Good morning. Thank you very much. The slides are being, prepared. I thought this talk is a kind of a project report. So actually, I summarize a little bit of our group work. Our team consists of actually 12 faculty members, PIs, and I have the responsibility to represent them. Yeah, so today I will showcase some of the work we have done recently during the last year. But in general, actually, we pursue very ambitious research goal, which is to build the ultimate learning machines. That's called the universal learning machines. So how we build a machine that can learn continuously online in real time in the real world. So maybe, okay, sorry, what was wrong? What was wrong? So yeah, so there should be some principles to do that, and actually I will not talk much about that, but I think I need to tell a little bit about that as a preliminary. So maybe for a machine to learn continuously, we need some principles or some components. One, I think, is a very important thing. That's the next level of machine learning, the embodiment. If the agent has a body, it can act itself and recognize the result of action. And so self-feedback is possible, which is not possible in current machine learning paradigm. So that's a fundamentally important next step of machine learning. That's called it's not machine learning, it's a learning machines. So that's why we will use always the sensors and actuators. So it's a really robot-like embodied agent. Another thing very important, I think, is multisensory data, multisensory. We humans learn not just from the single modality. The different modalities are complementary each other. So the really difficult thing is uncertainty. But if you have many modalities, the uncertainty can be reduced by complementing from another modality. When speech is not perfect, then the vision can help you. When vision is not perfect, the speech or audio sound can help you, or touch as well. So very much important multisensory integration. That is found a very long time in brain science, actually, in cognitive science. Another important property, I think, is the kind of a bootstrapping and bottom-up and top-down. So you learn from sensory data, very much data-driven now, and basically you build some higher-level abstract representation or knowledge. Knowledge is the ultimate goal of the AI, but also there are some uncertainties in the data, sensory data alone. So you have some complementary information from top-down inference, as well as a bottom-up. So that's a very much complementary each other. I think that's important algorithm for that, the expectation maximization algorithm, fundamentally important algorithm. So you learn from bottom-up data to build a higher level abstract representation. And on the other hand, from the top-down inference, you can estimate the other uncertainties. And so that kind of things together, basically we try to build the universal learning machine. So the title of the Group 7 research is a fully autonomous learning machine that continuously learns in the real world. So that's the topic of the Group 7 project, right? Yeah. So three important components: perception, action, and cognition. I have to emphasize again, it's not just important that we have each component, but it's in cycle, perception, action, cognition. Cycle is important. So that should be combined each other. So to predict the action, you need the perception and cognition as well as. So action is basically sequential, especially it's an embodied situation. So so perception, very much multisensory part I told you already, and cognition very much from bottom up to top down. So it's kind of a bootstrapping. We learn from what we already have learned. That's a fundamentally important principle in machine learning. But most current approach is based on just a batch style, big data, and but more important is we learn from the previous knowledge that was learned before. So, and that should be used for the next step of learning. So that's the more cognitive, in some ways, more like a self-reflective part of the learning. And again, action is very important because by action, you can learn yourself. No one can, so I can learn myself that this table, how is it heavy or not? And you don't need to tell me. I can do myself and try, and I recognize it, that it's not moving. So I know that this table cannot be moved. So no teaching is necessary if you have action and the body. So once again, very important principle. So generally, we have identified 3 important components of that research. One is once again, it's a more repetition and summary. So one part is the mutual cross-modal representation learning and associative inference, especially with the multisensory data. That's one part, more like a perception part. The second part is more like an action part. You have to act and interact with the environment and to acquire new data. So current machine learning approach is assuming that someone or some agent or some device can provide you the data. But the real important thing is what data you learn is more important. It's a kind of active learning. So the learner have to decide what should be learned itself. It's very, very important part of intelligence. Another one is effective knowledge acquisition and storage. So once you have a lot of data, multisensory data, and large data, then how you compactly represent the knowledge or acquire the knowledge. Kind of a compression is a basic underlying principles in almost all machine learning. Compression and kind of a distillation ideas. Compression is the, yeah. So this research is the 4th year, and on the 4th year now, the specific topic has been transfer and advanced knowledge transformation models for learned knowledge. Okay, so now, and the final report. So as I said, we are consisting of about 12 faculty members, and this year alone, we have published 60 papers in top tier conference. Just the number, I mean, the CAA AI, ACL, ECCV, EMNLP, ICASB, and so on. And actually robotics conferences as well. So now some samples of our research. One sample, I brought here actually 2 samples that all involved with very much with the language, vision, and interaction, vision, language, action part. So using robots, so you have the robot arm here and a lot of objects on the table. So basically, vision is there, and the robot arm has to move something, given some instruction or linguistic dialogue. So, for example, a basic idea is to manipulate some object manipulation. So, if the human says, my device runs out of the battery, it just says runs out of battery. It doesn't say what I needed. Right? It's implicit. It's a pragmatic problem in language. So, but it's ambiguous. There are two different batteries are there. So the robot AI asks, do you need a bigger charger? So smaller one or a bigger one? And then the humans answer, no, give me the smaller one. So okay, and then object grasping. So the robot gives you the smaller one. Okay, so that kind of a task cannot be solved by just one turn of dialogue, right? It needs a lot of many steps of dialogue, so turns. And by doing that, actually disambiguates some ambiguities. Very important. Again, as I said, so to learn something, you need to understand that. Understanding part is actually more difficult part, not just the estimation. And so basically here we try to give the agent some pragmatic inference capability. Pragmatic use of language. So what's the intention of the speaker, or what's the goal of the speaker? The agent should be able to infer that kind of intention. So that's the pragmatic part. In the previous example, it just showed that it just needed a kind of the battery is almost out, and then it intends to ask to give me the battery, right? So research question here has been how can robots reason about the user's intention from under-specified instruction, under-specified, there is some ambiguity, and grasp the desired object through interaction. So by doing action as well. So basic components has been basically visual grounding. So you have to recognize the objects in the visual image. Basically, we can use here the many foundation models like vision transformer or something like that as a pre-trained model now. And then you should ask, generate a question, and then also generate the answer, partial answer, and interpret that. So those are the components. And then finally, you should grasp the object. This is some preliminary research. Going back to the idea of ultimate universal learning machine, actually we should do after that as well. After grasping, it might be wrong, and then by the wrong grasping or action, you need to further ask other questions or recognize others. But this is just the first step toward that. By here, the disambiguation is done by just a linguistic dialogue, multi-turn dialogue. But in the end, as I said again, the turn multi-turn should be action as well. So just in video, some demo. Okay, there is no sound here. Just the user tells something. The progressive is the agent name, grasping. So if you say something, it sees the environment, and if there is, that should be, once again, let me go back. Okay, sorry, the sound is missing here. So again, it shows the dialogue first, and then after that it's moving. So, and then identify some candidate objects, and then disambiguate it, and once the goal object is identified, then it grasps. The next scenario, here another scenario. So there are two candidate objects again, something to eat, and then it disambiguate, and then grasp the final objects. So yes, of course, but some experimental results. So we do some offline experiments as well as online. Actually, in online, when you do really have a body and action, there should be more uncertainties. That's kind of a dilemma as well. So from machine learning point of view, if you add a body and action, I said that it's a good because we can get more information and I can get data myself. That's the good part. But of course, there is a trade-off. By doing that, you are adding more uncertainties, right? So the data is not, there are some more additional uncertainties. So at the current stage, especially, it's not, the final accuracy might not be very good. That's why many, I think the researchers and my students are a little bit hesitating to do the body-related work. So it's not sometimes easy. But I think, again, it's a fundamentally important next step of machine learning. It's a different dimension of the machine learning. So as you see here, actually, without grasping, anyway, the performance is much better, while the absolute performance is still very big, high, when you do real action, as you see here. It's around 50%. Of course, the grasping itself is not perfect. While you grasp the object, it can drop the object as well. Considering that, it's a real world performance anyway. I'm showing you here the absolute performance is still not perfect. Okay, maybe I should speed up. Another component, another paper is now, previously we used the language as a communication means. That's a typical thing. But language is a very good means to teach the machine, right? Instruction. So I will show you here that part. So here the language, so we can teach the machine by talking. And that's we call the long time learning by talking. So here is the example. So there are many objects like previous experiments. Then I can teach the machine personal information, like this object in front is my sleeping pill. It's my pill. It might be another person's pill in the family, but it's my pill. And then afterward, I talk to the agent that bring the medication I take to help me sleep. So my medication, I talk to them. There can be many different medicines, but the agent can give me my medicine, right? So that's another part. That means the AI has now some personal information and personal, we call the reminiscence here. It's kind of a memory, recall memory. So my personal information is also stored and then used later for service. So that's a kind of a very much a personal intention can be read by the AI. So talking is a very good means to teach the machine. So I should summarize. Actually, I prepared another work by Frank Park's lab, but I will skip another one object manipulation task. You can also building some. This is actually the Robotic scenario in the real living room. You have to navigate and do some manipulation objects, and we have been building some maps as well. So language designated map building, kind of preliminary work. Sorry, but I should skip. That's the lab situations. We have actually built small convenience shop scenario. That's and then built a map. And actually by language, you can designate the objects in the visual map, and then give some linguistic instruction or a question, then the agent, the robot can go somewhere, for example, without explicitly actually identify the object, but the robot can move someplace. Okay, another part, as a project report, we have open research in our group that's done by 3 professors. One is from medical school, Professor Kwon Jun-soo, and another one is Chang-gun Lee from computer science. And one institution is the company Toruk, a robot company, Dong-soo Chan. 3 of them work together to build a digital psychiatrist. It's basically AI agent that learns from human phone and behavior and actually do some diagnosis. So Kwon Jun-soo is a psychiatrist at Seoul National University Medical School. And recently they have also built Dr. Simon. It's more for students. When the students use the tablets or phones, they gather all the signals, multisensory data from the device, like a touch and the speed and the force of the touch, as well as eye tracking, all the multisensory data, and then try to diagnose or predict the mental state, and also diagnose some or recommend some feedback for the student or for the teachers or parents. So it's for the mental health care. It's done by the 3R, the company 3R, and the Toruk, the companies. It's being tried to commercialize. And final result, actually, we have been attending RoboCup for a long time. This year, we did the 3rd place. That's a little bit unfortunate, but last year we won the 1st place. This year, and 3rd place. That was SNU and the Busan National University collaboration team. Okay, I ran out of my time, and thank you very much. Yeah, thank you.
Thank you, Professor.
Okay.
For the great talk. So if you guys any questions, please raise your hand. Yep.
Thank you, Professor
비디오
Zhang.
이거 잠깐만 보여주시겠어요? 그래도 여기 마지막에 비디오가 좀 있는데. 네, 하시는 사이에. Yeah, thank you. 아니 그러니까 질문 받은 사이에 그냥 보여주세요.
So I could ask questions.
Right, that's the real RoboCup scenario. That's done in Netherlands this year. So it's kind of home situations. There are many leagues. We attended usually the home league, DSPL, domestic standard platform. And the robot here used the mobile manipulators from, you see here. You really need to do perception, action, and cognition, and navigation. Okay, thank you. Questions? You had the questions.
Okay, yeah. So thank you for the talk. And actually, I have a question about the first project you introduced, the GRASP. So the thing is, I think is, for the dialogue, I saw there's a lot of confirmation. Like I need to know, like, I'm hungry, and then you have 2 options, and then even I said like I don't like apple, but then I still need to get confirmation. Like the robot said, do you want banana? And then I said I want a banana. So I feel like it's like a huge trade-off between the accuracy and the efficiency I could get. Have your team ever considered about this problem?
So the second part actually complemented the first part by teaching the robot or giving information to the robot by another language. So to teach them. Of course, if you have a lot of objects and the previous context is not clear, there will be a lot of ambiguities, and you need maybe multi-turn dialogue to disambiguate it. Yeah.
So have your team ever think about the other possibility that you could actually use to improve the efficiency other than just like continually learning about what's happening here, since they have one-shot learning or they have some neural signal that could reflect it?
Of course, yeah. We have a lot of ideas, actually. We had another project called the Baby Mind. Actually, it's trying to learn from the children, babies, until 18 months. So they use a lot of different signals, like eye tracking or some kind of a gesture. Anyway, in this situation, still the robot can see the human partner and get a lot of different signals, okay, multimodality or multisensory. But we are not using that yet, not fully, yeah.
Thank you for the answer.
Thank you very much.
Yeah, let's thanks.
In the interest of time.
Yeah.
Thank you.